Chapter 6. Reuse. Section 1. User-defined functions. Still, suppose there is no factorial function. Now we want to calculate the number of combinations. Cnk equals the factorial of n divided by the factorial of k times the factorial of n minus k. N and k are filled in A1 and B1 respectively, and the second, third and fourth lines calculate the factorials of n, k and n minus k respectively. This calculation is okay, but the same code has been written almost 3 times. If the problem is more troublesome, for example, we need to calculate the coefficient sequence of the binomial theorem, that is, a line of Pascal triangle. The loop function can calculate multiple values in one statement, but it must be easy to write in the expression. If it needs several lines of code to realize the calculation, it has to use the loop statements. In fact, most programming languages, including SPL, allow us to write the code to be repeated as user-defined functions, and then call them over and over again. The func statement of cell A1 defines a function named factorial. Its code is the code block of A1, and n is its parameter, which can be referenced in the code block. When SPL encounters the func cell, it will skip this code block and execute the subsequent code. SPL will automatically register the self-defined functions, and then they can be used as regular ones. For example, the function is used to calculate the factorial of 10 in cell A3. SPL will assign the corresponding variable, here is the n, as the value of the parameter, and then let the program jump to function's code block, here is the A1, to execute, that is, start to execute B1 to D2. We can understand the code of B1 to D1, which can calculate the factorial of n and fill in B1. When n equals 10, this code calculates the factorial of 10, and fill it in B1. Then the return statement of cell B2 returns the value of B1. At this time, the program will jump back to the place where the function was called, that is, A3, and has already got the return value the factorial of 10 of factor 10, the cell value of A3 is the factorial of 10. That is to say, the user-defined function A1 will calculate the factorial value of its parameter and return it. Similarly, B3 will calculate the factorial of 4, C3 will calculate the factorial of 6, and finally, the number of combinations is calculated in D3. The whole process seems a bit complicated, but in any case, the 3 factorial values are calculated using the same code, and there is no need to write the code 3 times. To sum up, func statement is used to define a function, in which return statement is required to return the calculation result. Then use the defined function name to pass in the parameter to call this function. User-defined function is also a function. It can be used in the same way as other SPL native functions. It can be put in the expression to participate in the calculation. The result can be calculated correctly in this way. Moreover, after the user-defined function is defined, it can be used in the loop function. The calculation of binomial coefficients also looks clearer. Let's take another practical example, finding outliers in a batch of points on a plane. The method is to calculate the sum of the distances from each point to other points, and then sort them from large to small. The top 10% of the points are considered as outliers because they are relatively far away from other points. In A5, the user-defined function distance is defined to calculate the distance between 2 points. It has 4 parameters, which are the abscissa and ordinate of 2 points respectively. Using Pythagorean theorem, the distance between 2 points can be calculated. When a user-defined function has more than one parameter, just give them different names. Function definition can be anywhere, in front of or behind the main program will not affect the code execution. In the main program, the abscissa and ordinate of 100 points are generated randomly. Then in cell B2, the user-defined function distance can be called to calculate the sum of distances. This is a 2-layer loop function. The inner layer calculates 100 distances and the sum, the distance between one point and itself is 0, adding one more will not make mistakes, and we don't have to exclude the point itself, and the outer layer loops the 100 points. Note the difference between A2. And tilde in the inner loop. Then use psort to sort and get the sequence numbers of the top 10% points. Section 2. Recursion. With the user-defined function, we can write recursive programs. Let's look at the factorial operation. It is a good example. We know that the factorial of n is equal to the factorial of n minus 1 times n. That is, if we already know the factorial of n minus 1, we can use multiplication to calculate the factorial of n. However, special treatment is required when n equals 0, because the factorial of n minus 1 is meaningless at this time, and we cannot calculate the factorial of 0 by the factorial of 0 minus 1. Let's write a user-defined function to calculate factorial with this idea. In user-defined function factorial, it calls itself. This method of writing function code is called recursion. Let's analyze the execution process of this function. If the parameter is 0, then the condition of b1 holds, continue to execute c1, return 1, the function ends, no problem. By the way, when a user-defined function is executed to the return statement, it will be executed and returned, regardless of whether there are statements after it. If the parameter n is 1 and the condition does not hold when it is executed to b1, the cell b2 will be executed. At this time, n minus 1, that is, 1 minus 1 is equal to 0, will be used as the parameter to call the function first. After entering the function again, parameter n will become 0, and the n equals to 1 will be temporarily stored. Now that the condition of b1 is established again, it returns 1, and then returns to cell b2 before the call. The n stored just now is restored to 1, so it calculates 1 times 1 is equal to 1, and returns. There is no problem. If the parameter n is 2, it will also be executed to cell b2. At this time, n minus 1 is equal to 2 minus 1 is equal to 1 will be passed into this function as the parameter, and n equals to 2 will be temporarily stored. From the above analysis, we know that it will return 1, and then restore the value of n to 2. When the parameter is 2, the function will return 1 times 2 is equal to 2, which is correct. As long as the factorial of n minus 1 can be calculated correctly, the factorial of the current parameter n can be calculated correctly. Recursion is a bit like the mathematical induction we learned in high school. If we want to prove the proposition related to n, we need only prove 2 steps. 1. The proposition is true when n equals 0. 2. If n minus 1 is true, then n is also true. Recursion is also similar. If we want to do a calculation related to n, the direct calculation may be troublesome. So long as we do these 2 steps, 1. We can do the calculation when n equals 0. 2. If the calculation related to n minus 1 has been worked out, we can do the n-related calculation. We've just used the above method to calculate the factorial. Let's try the nth term of the Fibonacci sequence that we have done before. Its rule is as follows. 1. f1 equals f2 equals 1. 2. fn equals fn minus 1 plus fn minus 2. The code written recursively is also very simple. When this code recurses to n, it depends on the 2 results of n minus 1 and n minus 2, and there are 2 initial cases n equals 1 and n equals 2 to deal with specially. When writing recursive code, we must pay attention to judging the initial situation. If we forget this judgment, recursion will become an endless loop and never return, and this endless loop will easily lead to memory overflow. This is because every time the recursion enters the function body again, the current variable value will be temporarily stored for recovery when it returns. If the recursion does not return, the space occupied by these variables will soon exceed the memory of the computer. Careful readers can also analyze that it is not cost-effective to use recursive method to calculate factorial and Fibonacci sequence. The computation amount and memory of these 2 recursive codes are much larger than the previous loop method. Recursion is used here only as a teaching example because the logic is relatively simple and it is easy to understand the principle of recursion. Let's do another example that is difficult to do without recursion, calculating the full permutation of n. The full permutation of n means that the n numbers 1, 2 until n are lined up and all the different arrangements are listed. If n equals 3, there are 6 types, 1 2 3, 1 3 2, 2 1 3, 2 3 1, 3 1 2 and 3 2 1. If n equals 4, there are 24 types and the number of full permutation is the factorial of n. It's not easy to list the factorial of n types of permutations directly. It's easier to use recursion. 1. When n equals 1, there is only one type, that is, 1. 2. If we already have the full permutation of n-1, suppose it is a sequence P, which should be a two-layer sequence, and each member is a permutation. Now we just need to arrange n before its first, second until n-1's positions and append it to the last for each member of P to get n new permutations, then collect all the new permutations. Note that each member of P corresponds to n new permutations. Write the code in this way. When A1 is 1, directly return the result, sequence 1, and pay attention to return it as a two-layer sequence. When A1 is larger than 1, first prepare C2 to be an empty sequence to store the results. Recursively call this function to calculate the full permutation of A1-1, and then loop it. For each member, generate A1-1 new permutations in C3 to arrange A1 before the first, second until A1-1's positions and append it to the last to get A1 new permutations, and then concatenate these new permutations after C2. At the end of the loop, C2 stores the full sorting of A1 and returns it. Let's change the problem again, calculating the m permutation of n, that is, select m different numbers from 1, 2 until n to arrange. There are two parameters in this case, and the situation is a little more complicated than just now. Similar to the Fibonacci sequence, we need to call the recursive function twice. 1. When m equals 1, there are n types, namely 1 until n. 2. When n is larger than m, after we already have the m-1 permutation of n-1 and the m permutation of n-1, which are recorded by P and Q respectively, then as long as n is inserted into each member of P by the positions mentioned earlier, new m permutations can be obtained. Each P member corresponds to m new permutations, which all contain n. And then merging them with Q, which do not have n, thus getting m permutation of n. 3. When n equals m, just deal with P in step 2, which is equivalent to the full permutation. This section of code is a little complicated, but the difficulty is not the writing of the code itself, but to come up with this calculation method, that is, how to solve the problem mathematically. Let's recall what we said at the end of the loop chapter. Programming language can't help us find a solution to a problem, it can only help us realize the solution that we have already thought of. In order to see the process clearly, we wrote the steps separately. After we are proficient, the code can be more compact. The relatively complicated is C3, which is a two-layer loop function. The expression uses the inner hash and the outer tilde, resulting in a multi-layer sequence. B3 itself will return a two-layer sequence, each member is a permutation. C3 will expand each member permutation in B3 into a sequence composed of B1 permutations, so as to get a three-layer sequence, each member's member is a permutation. The conjunction function in B4 is used in a multi-layer sequence, concatenates the member sequences, and it is equivalent to performing sequence concatenation operation among all members. C3.conjunction is a sequence composed of B1 times B3.len permutations, and the expression to the right of sequence concatenation symbol is easy to understand. But it's really hard to understand. Sometimes it's not a bad thing to write longer code. Section 3. Reusable script. Until now, we've been writing code in a cell set. This cell set can be saved as a file with the extension .splx, which we call a script. Now we have learned to write user-defined functions that are called repeatedly, but this function can only be used in one script. After creating a new script, we have to copy it again. It is not like a library function that can be used in any script. How to achieve this effect of a library function? SPL provides a function to call another script in a script. Let's take the example of the code that calculates the outliers to illustrate how to do this. First, create a new script and then use the parameter function under the program menu to pop up such a dialog box. First, fill in the parameters of the script to be called here. Suppose that this script will receive the coordinates of a batch of points as parameters, calculate the sequence of outliers and return it. We designed three parameters. X is a sequence, storing abscissas, Y is a sequence of the same length as X, which stores ordinates, ratio is a proportion, which indicates how many proportion of the points with the largest distance are taken as outliers. The completed dialog box will look like this. The value column refers to the default value. When calling this script, If no parameter is input, this default value will be used. Here we just write a few. Now write the code in the cell. The script also uses the return statement to return the result. In the script, the parameters can be directly used as the variable names. In fact, if we execute it, we can see the parameters in the variable table at the bottom right. For SPL, script parameters and name variables are the same thing. Cell A1 uses the variable name of the parameters to determine the level of hash in a multilayer loop function. Save the script and give it a name, such as outlier.splx. Now, create another new script, which will allow us to call the script we just wrote. Use the call function to call another script and get the return value. It should be noted that this new script needs to be saved and stored in the same path as outlier.splx. SPL will generally look for the called script in the path of the current script. If the script has not been saved, there will be no path. If the path is wrong, it is likely that it will not be found. We have a default value when writing outlier.splx, so A5 can omit one parameter, and because we've used the round at S, A3 and A5 will return the same result. If the script still reports an error that it can't find the outlier.splx, it may be because the search path or main path is not written correctly. Use the Options function under the Tools menu to open the dialog box and switch to the Environment page. The search path may have been filled with inappropriate content, and the called script will be searched under this path first. The advantage is that we can write some common scripts and put them in this path, so a script stored in any path can call these common scripts, and there is no need to copy the called scripts to the path of the calling scripts. If the called script still cannot be found when the search path is empty, there may be an error in the main path. For file names, including script names, that use relative paths, isproc first searches the main path. When the main path is filled with blank, it will search the path of the current script. This rule is a bit complicated, and it is set for developing complex applications with many scripts. SPL also provides a register function to register a script as an ordinary function. When registering a self-writing script as a function, it is better to use the absolute path or put the script into the search path, otherwise it may not be found because of the different paths to call the script. Registered functions are valid for all scripts, not only for the current script. Repeated registration will replace the original. We can use a script to register other scripts that are commonly used to be called as our own functions. In the future, every time we start sproc and execute this script to register other scripts, it is equivalent to adding many library functions. The contents of the first 3 chapters, together with this chapter, constitute the vast majority of process control mechanisms of modern programming languages. Object-oriented languages also have overload mechanisms, but the content is abstruse, which is not covered in this book. These are the ways to control the flow of a program. Different programming languages may use different reserved words, but there is not much difference. When learning a new programming language, these flow control statements and data types are the basic contents. After this, the focus will shift to richer data types and corresponding functions, such as the sequences we've been exposed to before. Different programming languages have different usages, and they have different emphases in data types and functions. Different programming languages have little difference in process controllability, but the difference in data types and functions may be very huge. It can be said that data types and related operations constitute the fundamental style of a programming language.